Any general questions, problems, anything? So far, I've already been thrown out of the Zoom once, so keep your fingers crossed out there in Zoom land. Anything? I'm under 200 papers left to read, so please be patient. I'm trying to do 20 a day during the week and more than that on weekends, but it has been a challenge. Anything else out there? I did open up Project 3. It's on my courses. I sent out the link yesterday. Essentially, it's the equilibrium/thermodynamics portion of your same reaction. As you will find out next week, probably late next week, equilibrium is really more of a proxy for thermodynamics. Thermodynamics is the actual thing. So to that end, when I say thermodynamics/equilibrium, I'm really talking about the same thing. But again, it's one of those cases where depending on what subdiscipline your reaction might fall into, it might be more common to talk about the equilibrium side of things, or it might be more common to talk about the thermodynamic side of things. So you want to kind of keep both in mind. And the thermo part of it, some of you actually had thermo stuff in your papers already, so you've at least got references that have some, if not all, the information. But for those who don't, right, if you look for equilibrium or the thermodynamic piece of it, you should be able to piece that half of it together. But again, that's more a topic for next week, which is why Project 3 is not due for 3.5 weeks or something like that. But it's never too soon to start looking. Okay. Okay, then onwards and upwards. Again, we were talking about this little mixing problem. Right. Now, you know, on Monday, we were talking about solubility, right? And Ksp is really describing the solubility, right? And I don't want to completely negate the importance of that, right? But as I've been saying, the thing about the solubility is it's really just a point in concentration space, right? It's the maximum amount of something you can dissolve at a given temperature. And so as a measurement of solubility, that is what Ksp is, right? But it's not an equilibrium that's always in effect. And therefore, if I'm just talking about dissolving something, I really don't have to go through the trouble of solving the equilibrium problem every time I throw salt and water and stir. I can just as easily use the number as it's already been solved. And so for straight solubility, that is what I'm more prone to do. Where I do need to consider the actual equilibrium is more in the case of the precipitation, right? Specifically the precipitation that's driven by mixing two solutions together, right? Because again, I'm not going to precipitate from a solution that's just sitting there dissolved. It's either saturated, right, or it's not, right? And sure, it might be cloudy, and maybe I threw, 4 cups of sugar into my coffee, and most of the sugar is just sitting there in the bottom, right? But what does that tell me? Pretty much nothing, right? The solubility of sugar in coffee is, 110 grams per 100 milliliters. And so that's how much sugar is dissolved, and the rest is just laying there. It's still just a point in the concentration space, the maximum amount I can dissolve, right? But if I mix two solutions together, right, I can again, in some sense, much like, the acids and bases we were talking about, I can create accidental chemistry. Right. In the case of the acids and bases, the issue is that all acids will react with all bases. And so even if I'm trying to do a specific acid-base reaction, I can't stop the acid from reacting with all of the bases. Right. And to that end, I have to then carefully choose my acids and bases so I don't get that interference from other reactions. Right. In the case of KSP, it's the same basic issue, except it's not acids and bases, it's ions, right? And it's the same basic issue. Any positive ion can react with any negative ion. It's the nature of charge, right? And so again, depending on what my mixture really is, if it's an intentional mixture, right, this again is where my design can help prevent accidental reactions from interfering, right? And so I have to choose my salts carefully. And that's why, as we've mentioned several times before, I tend to use sodium salts because the sodium is a spectator and it stays out of the way, right? We talked about how and why it stays out of the way in acid-base reactions. It also stays out of the way in KSP reactions because of the high solubility of sodium or potassium salts, right? On the anion side, right, nitrate is the conjugate base of a strong acid, and so it stays out of the way in an acid-base reaction. But nitrates also tend to have high KSPs, so nitrates also tend to stay out of the way in KSP reactions, right? And so that's where my conscious decision about which salt to use can simplify the mess that might be my chemical soup by intentionally choosing things that will be spectators and therefore stay out of the way. Right. The last thing I want to do, right, is create side chemistry that's going to interfere with my primary reaction. Right. Most chemical reactions have enough problems. Right. Less than 100% yield, possibly hazardous side reactions, costs, et cetera, right? I don't want a whole bunch of other stuff going on that makes all of that worse, right? And so in this particular case, I didn't really provide any context for why I would mix these two things together, right? But if this was an intentional mixture, right, I can tell without any paragraph explaining what I'm doing that my whole point here is to precipitate iron hydroxide, right? If this is an intentional mixture, I know it because there's a nitrate salt, and I only pick nitrate because nitrate tends to stay out of the way. And there's a potassium salt, right? And I only tend to use potassium because potassium tends to stay out of the way, right? And we got as far as saying, look, right, salts dissociate. And again, since these were already solutions of potassium hydroxide and iron nitrate, they're already dissolved. And so those are not the two things that will precipitate. What is likely to precipitate is the brand new compounds that could form, that couldn't have formed before because they weren't all in the same beaker, right? I mixed two solutions together. This is the first time the iron met hydroxide. This is technically the first time the potassium met the nitrate. And so, you know, in a Chem 1 sense, there's at least the possibility of a double replacement reaction, right? In Chem 1, that became a very binary decision based on my solubility rules. Is it soluble or is it not? Right? In a Chem 2 sense, it's a more sophisticated question, right? Which is how soluble are they? And have I exceeded the solubility? Because again, you know, in actual fact, solubility is not really a binary decision, right? There's a whole spectrum of different solubilities, right? And again, the Ksp is the solubility, and that tells me what happens. And we got just about this far on Monday, which was I've got essentially 4 possible reactions, although right off the bat, I know to ignore 2 of them. But if I want to write all 4 down, I could, right? In the end, right, all 4 of them could happen. The special nature of Ksp is that unlike the acids and bases, some of them may not happen, right? Because I don't always get to Ksp equilibrium. It's only if I try to exceed the maximum solubility that anything is going to happen, right? And what's going to happen is potentially the precipitation. So as I was saying at the very end of class on Monday, one of the things about Ksp that tends to confuse the issue is the fact that it is an equilibrium that's not always in effect. Right? That's new. The other thing is that it's a little bit backwards. Since I'm mostly dealing with precipitations, it's the reverse reaction I'm talking about. Right? In that sense, my rule that biggest K goes first is still true, except biggest K for the reverse reaction is the smallest K for the forward reaction, right? And so I'm really looking for the biggest K precipitation, right? But the biggest K precipitation is the smallest Ksp. You know, I added 2 slides here, and they have disappeared in all of my computer problems, right? Ultimately, right, this is 714, right? This is one possible reaction that could happen in reverse because, again, this is the first time the potassium and the nitrate were in the same beaker. The other possible reaction that could happen is the iron hydroxide because, again, the iron hydroxide, same reaction in reverse. All right. In theory, they both could happen, right? If I've got so much stuff dissolved that I've exceeded the solubility for both of those compounds, they'll both precipitate, right? Ultimately, the test is the Q value, right? There is, right, there is a concentration of all 4 of those ions, which is technically a dilution of what they were separately, right? And so if I take the iron nitrate, right, it was 0.1 molar when it was by itself, but I've now mixed the 2 solutions together, so the total volume has gone up. And so the concentration of iron nitrate, he says with scary air quotes, right, because again, it has dissociated, right, but the concentration of iron nitrate is 0.0667, right, based on the fact that my iron nitrate dissociated, right, that really gives me 2 concentrations, right? If this is 0.0667, right, this is 1-to-1, so this is 0.0667. Also, there's 3 nitrates, right, per 1 iron nitrate. So this is technically, I can't quite squeeze all of it in, right? 3 nitrates per 1 iron nitrate, so 0.200 molar. If you do the math, right, the potassium hydroxide is 1-to-1, right? So this is the concentration of potassium. It's also the concentration of the hydroxide, right? And so ultimately, if I really want to decide if there's an equilibrium here to worry about, right, it's a question of what Q is relative to K, right? And so the Q, SP technically, of the potassium nitrate, right, is the potassium concentration times the nitrate concentration, right? Well, here's my potassium, 0.0333 molar. Here's my nitrate, 0.2, right? That is 0.00667. Right? That number is much smaller than 714. Right? So again, if my Q is less than K, I'm not at equilibrium. But I also don't have a way to get to equilibrium because I would need more solid. And I'm not throwing solids in solution here. I was mixing solutions. So there's no solid laying around to dissolve. And so, again, much as I would hope to happen as soon as I start using potassiums and nitrates, they tend to stay out of the way. Right. On the other hand, if you do the same thing with the iron hydroxide, the iron concentration is 0.0667. The hydroxide is 0.0333, right? And again, cubed because there's 3 of them, right? The QSP there, is what? Essentially, basically 1 times 10 to the minus 5 times 6.0, somewhere around 7 times 10 to the minus 7, right? Which is in fact much larger than the 10 to the minus 39, which was my KSP for the iron hydroxide, right? And so again, by the same but opposite logic, since the Q for the iron hydroxide is in fact larger, right, than the KSP, right, there's too many ions in solution, right? I'm not at equilibrium, but I can get to equilibrium because I do have the ability to form precipitate. I have both of the ions in excess in the solution, and so the reverse reaction is possible. Right. And so essentially that was all the prep work to get me to the usual familiar ground that, hey, I do have an equilibrium problem to solve, and all equilibrium problems have 3 parts. So now I've identified the only chemical equation I need to worry about, right? And so at that point, it's balanced equation, ice chart, K equation, solve. Right? Yes, no, maybe. Are we all confident at this point? Now I'd like to take a moment to issue a series of trigger warnings. 1, it's supposed to snow tonight. For some reason, as a longtime Rochester resident, I should be used to it, but somehow it's really pissing me off this week. I told my PChem lab that meets on Thursdays, if we literally get the 7-inch maximum they said we could get, I am going to stay home and sulk tomorrow, right? So say hello to winter again. It'll be spring again by the weekend, right? Chemical trigger warning, right? This might hurt more, right? You cannot make a simplifying assumption here because X is not going to be small hardly ever, right? In fact, you cannot, and this is the part that might upset you, you cannot solve this on your graphing calculator. You cannot solve this on Wolfram Alpha. Not easily, because you could only solve this numerically if you have software that keeps 10 or 11 digits in the number, right? If you solve this, I mean, it won't choke on it, but the answer it essentially will give you is that there's no hydroxide left in solution. Right. That's almost true, but it's not actually true. And depending on what my specific question was, if I care about how much hydroxide is left in solution, 0 is not the best answer. Right. Now, that doesn't mean I can't solve this. It does mean that here's a little algebra trick that, again, isn't really chemically specific, so it's not a bad trick to have in your toolbox, right? Which actually makes this relatively simple to solve rather than virtually impossible if I try to use some of my technological tools to solve it, right? And the issue, right, is that because K is so small, my suspicion is that X is technically really big. And so I'm going to make that assumption that X is really big, right? What does that mean? Well, what it means is it does mostly all precipitate, but I still want to find out exactly how much. And so what I'm essentially going to do is mathematically precipitate all of it and let it dissolve. Because here's the thing, and this is always true, by the way. This would have been true of any of our previous equilibria. We just never needed such a trick. There's nothing magical about this specific starting concentration, by which I mean I could move it around by doing the reaction. Again, this is more a theoretical doing of the reaction than a real doing of the reaction, right? But I could let this precipitate, which would change the starting concentrations, but as long as I obey the stoichiometry, it's an equivalent starting point, because the only thing that matters to get to the right equilibrium is that I have the right total amount of stuff, right? I can turn it all into solid if I want. I could even, God forbid, turn it all into the solid such that some of the concentrations are negative, because it's all really a theoretical starting point, right? And it will always get to the same equilibrium as long as I don't violate the stoichiometry, right? And so I'm going to mathematically precipitate the maximum amount of the iron 3 hydroxide and then let it dissolve its way back to equilibrium, right? And so to that end, it becomes a limiting reactant problem, right? Because again, that's what it means for X to be huge, right? It's so big that it essentially removes all of the limiting reagent, right? In this particular case, the limiting reagent is the hydroxide, right? One of these two things has to be 0. Whichever one is the smaller X that gets me to 0 is the limiting reagent. And so the hydroxide is a limiting reagent, which makes X 0.011, right, which makes X 0.011 everywhere. Right. And so essentially, I have precipitated, again, theoretically precipitated, the maximum amount of the iron 3 hydroxide, which leaves me with no hydroxide, less iron, right? And technically, again, the number doesn't really appear in my equilibrium, but I don't want a question mark there. I wanted quotation marks here, right? There is some iron hydroxide solid. I'm going to write it as a molarity because my ice chart is in molarity, but of course, it's a solid, so it's not really dissolved in solution, right? But the important point is I now have solid, and so it can dissolve its way back to equilibrium. It's now not at equilibrium because the Q is now 0, which is definitely less than 10 to the minus 39. But unlike before, it's less than, but I have a pathway to get to equilibrium because I have solid that could dissolve. And so essentially, I just now solve my K equation, right, as I normally would, but with my new starting amounts. At this point, if you care, Wolfram Alpha should work again. Your graphing calculator should work again. Or, you know, how much I love my assumption. My assumption should even work again, right? Because I've set the starting position knowing that X was really, really small. So X should be really, really small relative to 0.056. And so if I make that assumption in the corresponding substitution, you know, divide by the numbers, take the cube root, I get, in fact, a number that's really small, right? As I expected in the first place. Right. Yes, no, maybe. All right. And of course, once I have my X, it goes back in my ice chart. And, you know, depending on what the specific question might be, somewhere in my ice chart is the answer. If I care about the amount of precipitate, it's essentially the 0.011 molar. Right. If I care about the iron or the hydroxide, there they are. Right. Again, if I'm talking precipitate, it's not a real molarity, right? It's essentially the number of moles of solid that will precipitate out of solution per liter of solution. And so again, since it's a solid, it makes more sense to really measure it as a mass or something similar, because molarity is really kind of fake if you're not dissolved, right? And so the total solution volume was 0.75 liters. And so if 0.011 moles will precipitate per liter, right, and I have 3/4 of a liter, that'll tell me the moles that should precipitate, and the molar mass of iron 3 hydroxide is 106.9, right? So a better measure, which doesn't work in the ice chart, is grams for the solid, right? And again, if I care about the two compounds in solution, there they are. Yes, no. Again, it's a pretty neat little algebra trick, and it would technically work for pretty much any ice chart if you felt the need to reset the initial conditions. Right. For the most part, it's never really been an issue with our other ice charts because, again, they all had a pathway to get to equilibrium, and especially for my Kas and Kbs, right, the tendency most of the time was for X to be small, right? But if you think of some of those reactions we had where the assumption failed, right, some of those might be solvable doing this, which essentially is to take it all the way in the reverse direction and then assume X is small. That won't work all the time. There's a middle region where it's not quite significantly small, but it's also not significantly large. But for some of those failures we had of the assumption, this might work, right? But again, if you've got access to technology that can solve your equations, you don't necessarily need the trick, right? And again, it's worth emphasizing, right? My added step in these problems is really a test of whether I even need to solve my good old three-step equilibrium problem. I don't necessarily have to, and the Q test should always be my test. I can't always just look at the number for K, right? Here's two randomly made up Ks, right? I've got a larger KSP of 12 for XCl2, right, relative to a smaller KSP for YCl, right? And so, you know, in general, the bigger the KSP, the more soluble it is, right? But in fact, this is more soluble, even though it's the smaller number, right? Because of the stoichiometry difference. If I actually solve for the solubility, right, this is actually the solubility, and it's 1.44 for the 12, but it's 3 for the 9 because of this difference in stoichiometry. One's a 3-part salt, one's a 2-part salt. So essentially, one's an X squared KSP and one's an X cubed, right? And so to that end, right, I should always be doing my Q test because I can't necessarily tell just by looking at the numbers. Yes, no, maybe. I was going to say I want to come back to this, but maybe not. Okay, so, right, that was mixing two solutions where I had total control of everything, and I'm using my KSP, which essentially is my solubility in pure water, right? It's worth pointing out, right, that the KSP doesn't exist in a vacuum. And because of what we said about salts, right, my KSPs cannot be separated from acids and bases, right? Because a salt, when dissolved in water, dissociates, and when it dissociates, I always get an acid and a base, right? Because my cation is always the conjugate acid of some base, and my anion is always the conjugate base of some acid, right? It's semi-obvious if I use something like calcium hydroxide, because right? Again, when I play my little game, what kind of compound is that, right? The answer could be base or salt, but of course, salt is really an acid-base determination itself. And so what that means is, for many, if not most salts, there's a pH dependence of the solubility, right? And so if I'm dissolving calcium hydroxide, right, my Ksp reaction is like so, right? But again, my pieces represent an acid and a base, right? For this particular salt, right, if we think of it as a salt for a moment and don't try to do any acid-base chemistry or Ksp chemistry quite yet, right? The issue is always, right, what the K is, right? Calcium is the conjugate acid of calcium hydroxide, right? So this is the conjugate of a strong acid. And so the calcium is also an acid-base spectator. And of course, the hydroxide is straight up hydroxide. It's actually a strong base, right? And so, right, the existence of the hydroxide makes the solubility of calcium hydroxide pH dependent. If I have a separate base in the solution, right, that's essentially going to give me an initial concentration of hydroxide. Let's call it Y. Right, which actually makes it less soluble, right? Because I now have essentially an excess amount of hydroxide. Getting me to equilibrium means I'm going to have less relative calcium in there. On the other hand, if I had a separate acid, my acid is going to decrease the amount of hydroxide in solution, and so I'm going to tend to dissolve more calcium hydroxide to get to equilibrium, right? And so this salt will show a definite pH dependence on the solubility. Right. And that's something of a general rule, right? The only real exception, again, is if you have something like potassium nitrate. Again, technically speaking, right, when it dissociates, I have a conjugate acid and a conjugate base, right? But the potassium nitrate itself, right, is a neutral salt because this is the conjugate of a strong base, and this is the conjugate of a strong acid. As a result, they are effectively non-acids and non-bases. And so something like potassium nitrate should not show a pH dependence in the solubility, because even though there's technically a conjugate acid and base there, they are infinitely weak. Right. Yes, no, maybe. That makes sense. Right. In this mixing problem that results in a precipitation is, again, right? The problem I most frequently solve here, right? The solubility in pure water, hardly ever. If I want to know the solubility in not pure water, right? Right. If there's something other than calcium hydroxide in there that has acid-base problems, technically acid-base properties, technically I'm going to have to solve the K equation to see what the new solubility is. Right. If I do that, it's really just chemical soup again. Biggest K goes first, and as you've seen, you know, a lot of these KSPs tend to be kind of small relative to my normal KAs and KBs. So most of the time, though not always, right, the Ka or the KB goes first, but it's still the usual strategy of, you know, list all my reactions, find all the Ks, solve them biggest to smallest. All right. Except in this case, I'm going to have two different kinds of equilibria. There's the K acid bases, so Ka, Kb, or K neutralization, and then there's also the KSPs that will squeeze in there wherever the K puts them, right? But again, the more frequent problem here is really the mixing problem, right? Where the calcium came from somewhere and the hydroxide may have come from somewhere else, right? Because again, the equilibrium itself does not know where the calcium came from and doesn't care. It doesn't know where the hydroxide came from and it doesn't care. If they came from the same source, it's just the solubility, which again is typically my Wikipedia number, right? But where I have an equilibrium I might need to solve, right, is where I have a mixing problem where the calcium and the hydroxide came from two different places. This is not simply an academic construct, right? I mean, if you think of a couple different things, right? Right. I mean, if you're doing chemistry, what are you doing? Typically mixing reactants to do chemistry. My chemistry doesn't have to be precipitation. We'll talk apparently mostly on Friday, but in a couple minutes about when my intentional chemistry is precipitation. But the fact is, if I am doing chemistry that involves hydroxide, so a basic solution, and calcium, I need to be careful, right, about my choice because I don't want my reactants precipitating from the solution because then they won't react, right? And so even if it's not my intent to do a precipitation, the nature of chemistry is to mix reactants together, and I can't make them do only what I want them to do. Which means even if I'm doing some kind of synthesis, if there's acids and bases involved as reactants, they're going to also do acid-base chemistry with each other, which is going to lower my yield of the reaction I want. If there's ions involved, they're also potentially going to do Ksp reactions, even if I'm trying to synthesize something. And that's also going to reduce my yield, right? And so a lot of the chemistry that chemists do, right, is trying to maximize their yield by minimizing side reactions, right? And so for that reason, this idea of having precipitations from these mixed solutions is a frequent problem for a practicing chemist because, hey, that's what we do, we mix things. Right. For those of you, especially where's my civil engineers? This is a common intentional, unintentional mixing right? That happens even in your house, right? When you pour something down the drain, it all goes to the same place, right? Somewhere in your house, the drains mix, and then they go out in the street and they mix with your neighbor's drains, and then they get to the water treatment plant and they mix with the drains from the entire city, right? And if you get the wrong mix of ions where precipitation becomes possible, in plumbing terms, this is referred to as scale. You can literally form an insoluble rock on the inside of your plumbing. And so, you know, if you've ever seen a cross section of an old pipe, right, a lot of times there's all this crud and the effective diameter of the pipe has been reduced greatly, right, by the buildup of scale. And so this is not only a real chemistry problem, it's a real plumbing problem. And I only call out the civil engineers because you do talk about wastewater and effluent in at least one of your courses in your discipline. And then there's also what's really something of a physical process done chemically, which is what's known as a fractional precipitation, right? I can actually use the limited solubility of certain salts as a way to remove ions from solution. Right. I can do that for really one of a couple reasons, right? Right. One is as a method of purifying the solution. This is one of the ways that hard water treatment plants in your house work. Hard water, for those of you who don't know, and why would you, right? Hard water just means high metal ions. Right. And so one of the frequent ways to treat hard water in your house is to actually precipitate the metals, usually with hydroxide. All right. And that's why I refer to it as purification. Right. And the other reason to do it is for isolation, meaning if you've got gold ions in solution, you might want to get the gold ions out of solution so you can make a gold brick, right? And one way to do that is to precipitate them. This is in fact how strip mining typically works, right? And so after roughly 36 hours of winter, on Friday, we will look at the fractional precipitation problem. Questions or problems? Okay, otherwise, happy Wednesday.